Last class we were talking about waveguide structure, particularly optical fiber, right? We were discussing about. So, in case of optical fiber, we learnt about how right electromagnetic wave propagates, so optical fiber has a core with with a refractive index, let us say N1, a clade with a refractive index N2, and electromagnetic waves or optical light will get coupled through external medium. So, with refractive index in air, let us say air or some other medium with refractive index N0. Now, we know that the relationship between N1 and N2, where I had committed mistake, that N1, which is the refractive index of the core, should be greater than N2, right. By mistake I had written other way around. So, this should be. Now, what is the difference in general in case of an optical fiber, which generally we use quartz based optical fiber or SiO2, okay, SiO2 base. So, core will have different refractive index. How is it possible? By doping germanium oxide, okay, GO2, okay, coupled with this. Okay. So, doped. So, it's a doping, very small amount of right germanium oxide doped silicon SiO2, nothing but the quartz is the core, and clade is nothing but SiO2, right. So, refractive index difference will be there, and N1 is greater than N2, which allows optical light propagation. We also derived the relationship between means we also understood that refractive numerical aperture, right, plays an important role, and numerical aperture we derived, correct. Numerical aperture is basically it represents the sorry, N1 square minus N2 square, right, related, right, it is represented by this form, right, this numerical aperture is this. I am not deriving this form, but we know numerical aperture is, or maybe I will just show you this also, so that we will be in the same path. So, what I explained, numerical aperture is, it represents the acceptance angle within which the light can be coupled to the fiber, and in turn this light will propagate through this medium, through the optical fiber or a waveguide, without getting leaked out of this core region as far as possible. This propagation, how exactly it happens, you can go back to the optics and try to study. However, the electromagnetic waves, which are traveling this, electrical, let us say T wave, transverse electric wave is traveling in this way, and then it will get over here, phase change, and it will get reflected. And so, various these waves which are traveling will interfere with themselves when and the resultant at the direction of this propagation along which the light is basically going to travel, right. So, let us say this is Z propagation direction resultant through the optical fiber, although the electromagnetic waves are traveling in this direction, at an angle theta with respect to the normal of this incident, and it is traveling. However, the resultant electromagnetic wave will propagate, which is generated due to the constructive interference between these waves and the corresponding same waves, right, at different positions along this, right, wherever they are reflecting, and there will be, right, interference, and that interference will gives the propagation direction along this. Okay. And always remember that interference takes place between electromagnetic waves when they are having the similar polarization state. Okay. And of course, the wavelength should also be very nearer or same, right, then only the interference will take place between them. Over and above, so same wavelength, same polarization state in when they are traveling through the medium. Let us say waves are traveling through the medium. So in this, right, in this medium, when it is traveling, we will not be able to observe this effect, interference. It only we will see the interference when there is a, right, obstruction or scattering there, right, in the medium, right, in the at the interface, we will be able to see the interference. Okay. So when electromagnetic waves are traveling through this optical fiber, as it is, we will we will not see the interference, but at the interface, right, where it is reflecting, etc., there will be interference with its own waves, right. Constructive interference will result in the electromagnetic wave propagation along this, right, direction. Now numerical aperture also gives us the indication about acceptance angle within which, right, it should be. Now here NF stands for maybe I should have mentioned, maybe here it is core, NF is core, NC is clade. Okay. So refractive index of core is more, refractive index of clade is less. N0 represents the refractive index of the, right, external this medium, and theta 0, that is half of the acceptance angle, right, is related to the numerical aperture, okay, of this. Now when this electromagnetic waves propagate through this such a waveguide, here in this case optical fiber, etc., waveguide, the coupling of this energy or intensity, coupling or electromagnetic wave intensity, right, etc., may be different depending upon the type of optical fiber. So if I try to show you the fibers, there are different types of, based on the different types of waveguide structures or optical fibers. This is an optical fiber which is multimode fiber. Here you can see this is core, okay, this is core, and this part is the clade outside, right, region, and the refractive index in the core is something like a step index. Okay, so refractive index is constant within the core, refractive index is constant, and then it changes, right, in the clade region, which decreases. Now what makes the optical fiber as the multimode? What is the meaning of this multimode, right, fiber, etc.? If we see in terms of ray optics, just very general way of right, observing this, we can see this over here. You can see that the refractive index is so the ray which is traveling at a which is entering at a particular angle theta will travel with different, right, this angle, while another ray is traveling with, right, different angle. The ray which is, right, propagating on this, right, through the center of this core will travel with, right, different such angle. Now in terms of their electrical field and corresponding intensity, the electromagnetic wave which is propagating may be different, okay, through the medium. Some of this, depending upon their this angle, they may observe different losses when they are propagating through the fiber, and they are all known as corresponding to that either there will be a Gauss means zeroth order mode or first order mode or second order modes, etc., and indirectly they represent the intense variation in the electrical field. So, in terms of intensity, let us say the first order mode may have maximum intensity coupled with it in the center almost, right, while the second order mode may have slightly a different, right, intensity distribution in this optical fiber, etc. So, different modes have different such intensity distributions, okay, in terms of electromagnetic intensity. When they are propagating through the medium, because of its interaction with core as well as clade as well as interface region, this wave this intensity patterns, right, profiles are generated when they are propagating through this. And what happens basically, all these modes have different, slightly different characteristics in terms of their propagation, or their propagation through the optical fiber. And what we will see, if we see in a physical mode, let us say different angles the light. So, what you, as it is what you can expect, the light which is travelling through the center maximum will be travelling with a short period of time, no, as compared to the time taken by the light ray travelling this way at an angle, correct. It will, so the center part through which the light is travelling as it is will take the least time to travel through, while some other light rays will take little longer time. And that means my input here, if there is a, in terms of temporal, right, time scale, my input is single pulse, what will I see here is pulse broadening, I will see over here. Why? Because some part of the light will travel fast, will reach right early, while some part of the light which is travelling slow will reach little later, right, little later, some part of the light little later, and then, so the overall pulse broadening you will see. Okay, this is a schematic diagram, please do not follow the magnitude as it is, but you will get the idea that every light, this thing will travel, let us say it will take t1 time. So, this pulse will be t1 time, the other pulse which is, right, t2 time, t3, all will add up to give you a some, right, disperse or distorted, right, wave form output. So, input is single pulse, output may be broadband, right, a single pulse, etc. It is possible. So, this type of fibers which are known as multimode fibers. Okay. Now, this multimode fiber characteristics are decided by certain parameters. The parameters are wavelength of the light which is travelling, core diameter of this fiber, core diameter, okay, core diameter or core radius, whatever way we can, right, core radius of this fiber, etc. This will decide, as well as numerical aperture or refractive index of core and clade, correct, clade, which decides the numerical aperture of the fiber, right, numerical aperture of the fiber. So, these parameters, they decide whether the fiber will act as a single mode fiber or a multi-mode fiber. What is the meaning of single mode fiber? Here, in case of a single mode fiber, we will see that predominantly, okay, around 95% of the right intensity will be taken care, means the distribution of intensity of this electromagnetic wave will be within this Gaussian 0 mode, right, TM00 mode. So, most of this intensity will be focused on a single mode of the single mode propagation of the light. That means, theoretically, if there is an input with pulse with time t, the output will also have almost similar, right, time t. Of course, due to the refractive index coming into picture, there will be some dispersion coming into picture. However, if we do not consider dispersion, as it is the propagation, if we consider the electromagnetic wave will be travelling with a single mode, wherein intensity will TM00 or basically Gaussian 00 mode will be carrying the maximum intensity of the light. And this multi-mode or single mode fibers, what particular parameter decides this, we will see it in the next slide, but it is determined based on wavelength, core radius and numerical aperture values. Okay. Now, there is a way to correct this basically pulse broadening effect of the multimode fiber by introducing gradual variation in the numerical aperture, okay, gradual variation in the numerical aperture, okay, such that the light which is travelling at the interface, right, will be travelling with a lesser refractive index, although it will be propagating with longer distance, through longer distance, but refractive index is less as compared to the light which is travelling in the center, which is travelling with a higher refractive index comparatively, although the distance to be travelled is shorter, isn't it. So, indirectly both this modes, one travelling right near the core clade region along this, right, will be travelling with a longer distance, but with faster rate. So, the pulse broadening, right, will be minimal. Okay, the pulse broadening over here will not be significant, it will minimum, not like in case of multimode fiber where the pulse broadening comes into picture, because the path to be travelled is different by this different right modes of the light travelling through this optical fiber, although they are all observing the same refractive index. So, speed of the light travelling through this is not much different when you consider multimode fiber for all these different modes, while in case of dispersion shifted, okay, fiber, it is possible to right confine the pulse broadening, right, via refractive index change, right, this. Now, if so same thing whatever I described. So, input pulse is this, output pulse will get broadened, okay, right, in case of a multimode fiber, okay, in case of a multimode fiber, and that is obvious because the refractive index with which the light is propagating is the same. But if I change the refractive index of the medium vary, right, in a way that the pulse broadening can be minimized, okay, through graded index fiber or dispersion shifted fiber, correct, dispersion shifted fiber or graded index fiber, okay, optical fiber. This is also a multimode fiber, it allows multiple modes to propagate, but they all propagate such a way that the pulse broadening is minimized. If it is a single mode fiber, it will allow only single mode to travel through, and hence the pulse broadening is minimized, it only depends upon the dispersion coming into picture, okay. And what these numbers mean? Basically what it means that let us say if the this spectral broadening, this not spectral broadening, I am sorry, the pulse broadening right is considered. So, basically it can be represented in terms of right spectral, right, dispersion based spectral broadening. So it can travel, let us say 20 kilometer. When light travels through the multi-mode fiber, it may get broadened by 1 megahertz, okay, 1 megahertz, okay, broadening takes place. While if the light travels through the single mode fiber, even means it can travel for up to 1000 kilometer with only broadening of 1 megahertz, right, as compared to if I am using multi-mode fiber, within a short time the pulse broadening comes into picture, because right, the dispersion and all these effects will end up with spectral pulse broadening. While if I am traveling with using a single mode fiber, if the optical light is traveling with a single mode fiber, we will be able to see that for a longer distance the light can travel with a very small amount of broadening, okay. And if it is multi-mode dispersion shifted or graded index fiber, this number, right, can be improved to certain extent, right, few hundred megahertz or so. Okay, now another parameter, this multi-mode fiber is decided based on a parameter m. Okay, m represents number of modes which can propagate through the fiber, right, and if it is represented by another parameter which is nothing but the V parameter, okay. It's a relative basically frequency, right. This V parameter represents basically normalized frequency distribution, okay. However, for us V is nothing but 2 pi r divided by lambda 0 into numerical aperture, okay, where r is the core radius, okay, of the core radius, and lambda 0 is the wavelength of the electromagnetic wave, okay, wavelength. Numerical aperture Na is nothing but numerical aperture, okay. So numerical aperture is nothing but, right, if the refractive index of the external medium n0 is 1, then it is nothing but square root of, right, core refractive index square, core minus plane, right, square. This is estimated like this. So if this V parameter, okay, is less than 2.405, this parameter less than or equal to 2.405, then right, this although if you estimate with 2.405, let us say it will have 2 to 3 modes, but basically 90% or more intensity is focused in the 00 mode, right. So this fiber with V less than 2.405 is known as single mode fiber, okay. When the value of V is greater than 2.405, the optical fiber is treated as a multi-mode fiber, okay. So this if you go through any textbooks related to optical fibers, you will be able to know better. For us, it is very important to know that, okay, multi-mode fiber allows right, various frequency components to transmit through. However, we end up with pulse broadening. A single mode fiber can also allow various frequencies to transmit through with the cutoff wavelength determined by this parameter V, and if the wavelength of the right light is right, is based on this value V less than or equal to 2.405, that particular electromagnetic wave will be able to propagate through the optical fiber as a single mode transmission, right. So that is important parameter. So so you can also determine, if you know, let us say in a quartz optical fiber, let us see one just to get an idea. So, what is V parameter? It is nothing but 2 pi r divided by lambda 0 into numerical aperture. If we consider quartz fiber, okay, quartz fiber with n of the core as let us say 1.5, okay, n of the clade let us say 1.49, okay, and core diameter let us say 60, core radius or core diameter 60 micrometer. So, core radius is let us say I am just taking roughly, right, 30 micrometer. Wavelength, and let us say wavelength is, I am trying to find out if the wavelength of the electromagnetic wave which is propagating through this medium is 1500 nanometer, whether it will allow multimode, right, generation when the light is propagating through this, and it will end up with a as a multimode fiber, this optical fiber we can easily estimate, correct, or indirectly if I know the core radius numerical aperture values, I can estimate that what should be the wavelength of the fiber which will be basically wavelength, cutoff wavelength, such that the single mode transmission is possible, correct, either way it is possible. So, from this we can easily estimate what is V. If it is less than 2.405, less than or equal to, it is a single mode fiber, we can, right, derive like that. Now, so one more aspect related to optical fiber is its optical loss, okay, coming into picture, optical loss in fiber, okay. So, there are different losses which are encountered when the electromagnetic wave is propagating through the fiber. The one which is important is the Rayleigh scattering, okay, Rayleigh scattering, and it is prominent, as we already know. Rayleigh scattering is prominent when the wavelength is, right, is shorter wavelength, right. In case of a shorter wavelength electromagnetic wave, Rayleigh, right, scattering is prominent, because Rayleigh scattering is right inversely proportional to the, right, lambda raised to 4, where lambda is nothing but the electromagnetic. So, if this wavelength is shorter, the Rayleigh scattering will be large. Rayleigh scattering will in turn, if it is large, the light will, right, get lost due to the scattering effect. The second effect which comes into picture is the material absorption. So, quartz material absorption means the, here what is the meaning of material? It is an optical fiber material, right. Optical fiber material will decide, right, the losses, absorption losses coming into picture, okay. Now, if we see in terms of this material absorption, that is based on the material characteristics of the fiber, and generally let us say light with an intensity I0 is getting transmitted through the medium with a wavelength lambda, then the transmitted light intensity, the relationship between this is given by right, Beer-Lambert's law, right, Beer-Lambert's law. Subsequently, we will at some other point of time we will try to see what, right, this Beer-Lambert's law really is how it is right important and useful, as well as how what it means is. But here as per B.L.Lambert's law, the transmitted light intensity is related to the input right intensity I 0 lambda with a factor let us say alpha into z, okay, z, where where alpha is known as absorption coefficient, okay. So, unit, as you can easily understand, it is 1 per centimeter or 1 per meter or millimeter, etc., correct. Z is the distance it is traveling right through the medium. Sorry. So, it distance traveling through the medium, it is also unit right accordingly, centimeter or meter, millimeter, etc., accordingly. So, this is now this alpha is it has various aspects, but it is based on material characteristics, okay. And depending upon wavelength, okay, the alpha values will be different, okay, depending upon the wavelength. So, in case of quartz material, quartz, however, just to give you idea that based on alpha this based on lambda wavelength, the alpha value for right quartz SiO2 material is something like shorter wavelength absorption is large, then it decreases, and there are some other peaks, okay, and then it grows. So, this some of this where the alpha value again becomes prominent. Sorry, maybe once again I will draw exactly like this, it is okay. So, what it means near 1 point right approximately 1.3 to 1.5 micrometer, this absorption losses are very less, okay. And when we cross, if this is about quartz right material, and when we cross a certain wavelength right where this peak comes up right, it is because of the water particles absorption due to water molecules, etc., and other SiO2 material, etc., and this corresponds to in case of SiO2 it is some absorption right coming into picture in this wavelength. What is the wavelength range? Maybe around beyond 1.5 micrometer, okay, it is greater than 1.5 micrometer, and then it increases this absorption, okay, it increases. So, what it means if our wavelength of the light is optical wavelength is short enough, two aspects comes into picture. Rayleigh scattering is also large, Rayleigh scattering is large, as well as absorption parameter is also large and losses are large, okay. But as the wavelength increases, the Rayleigh scattering starts decreasing and even absorption is also decreasing, okay. So, maybe if I show you in terms of lambda micrometer and this is a fiber loss, okay, then it decreases as the wavelength increases, the fiber loss decreases. Due to the Rayleigh scattering it decreases, and due to material right it decreases, and then material absorption starts increasing. So, again it increases. Okay. It increases. So, this wavelength range is around 1.5 micrometer, this is maybe around 1 micrometer, this may be around 2 micrometer. Okay. So, you can see that if we are using quartz fiber, it has the absorption or fiber loss based on that, the characteristics somewhat like this, correct. So, there is a wavelength range wherein the losses are minimal, okay, through the fiber. So, this wavelength range is from maybe near infrared range 800 nanometer or 1 micrometer till mid infrared range at around 2 micrometer or so. Okay. So, when we consider optical electromagnetic wavelength, electromagnetic frequency or electromagnetic wave, with wavelength range, okay, maybe let us say 400 wavelength range less than 380 nanometer or so, 380 nanometer, it is known as UV, right, ultraviolet wavelength range, UV range. If it is 400 to 700 nanometer, it is known as visible range. When the wavelength range is beyond 750 or so, 750 to around 1.5 or it's this values may not be perfectly right in same, but within this range. Okay, I will put 2000, it is a little wider, but near infrared range, near infrared, okay, range. Okay. Beyond wavelength, beyond 2000 or between 2000 and 5000 or 7000 also, maybe 8000 also, let us see 8000 nanometer, right, it is known as mid infrared range, mid infrared. See, this is very little vague, okay, but depending upon books it may be different. Lambda beyond 10 micrometer or 10 micrometer is far infrared range. Okay. Now, in UV also we have less than 200 nanometer, okay, maybe 190, less than 190 nanometer, it is vacuum ultraviolet. Okay, vacuum ultraviolet. So, if the wavelength is UV range between let us say 200 and 380 nanometer or so, and then less than 200 nanometer vacuum ultraviolet, VUV we say. Why? Because see, many of molecules in the air will be having a prominent absorptions in this, right. So, as soon as the wavelength goes below 200 nanometer, oxygen absorption becomes very prominent, all those molecules in the air, which is plenty of molecules, correct, oxygen. So, they will absorb this light, okay, UV light. So, that is why we need vacuum in order to allow this light to propagate, that is a vacuum ultraviolet. There is one more range less than 13 or 15 nanometer, okay, 13 is extreme ultraviolet, EUV, okay, extreme ultraviolet range, etc. We will not go to those details, just I am trying to give you. So, here what we will see in case of optical fiber, we will be fine with SiO2 fiber when we are operating in the wavelength range from in the maybe slightly nearer to the visible 700 800 nanometer to 1.5 micrometer 2 micrometer, losses are less compared to when we work in UV range or when we work in infrared range, the losses are large. UV range losses are because of the Rayleigh scattering is prominent, and in UV in infrared range it is material absorption is prominent. okay, material is prominent. Okay. So, now of course, what we will be using optical fibers may be of a smaller length, this losses may not be so much, but still this losses plays an important role. Now, there is one more way to represent this losses. I showed you the B-Lambert's law, and I told that this is the way that the intensity variation can be estimated based on, if I know the alpha value for the material at a particular wavelength lambda, I can estimate that how this losses, right, as the distance changes increases, how this intensity variation will come into picture, transmitted light intensity. Now, this can also be represented in fiber by the another formula, which is given by losses are represented by decibel, okay, decibel minus 10 log of P0 by Pi, okay, and this is the way. P0 is nothing but the output power, okay, from the fiber, output power from the fiber, okay, power, and Pi is nothing but the input power, okay, and dB is, no, it is nothing but the decibel, okay, decibel. It is very similar to the sound waves, no, it has been derived based on similar way, and this formula is also indication, okay. This decibel can be represented by, right, alpha into L. Now, this alpha is not the one which I described in the previous case. This is right, it given means represented based on the decibel as the loss, okay, alpha. So, if I see this equation, what it means, PO divided by PI can be given by 10 raised to minus alpha L divided by 10, okay, where alpha is the loss parameter, it is right, loss parameter in terms of right, per meter decibel, right, per meter or per centimeter or meter inverse, etc. L is right, centimeter or meter, etc. Right, it is given by this. So, in case of optical fiber, okay, slightly, right, the values what I showed you over here as the Beer-Lambert's law, alpha parameter here is, it represents loss. However, it is indirectly in an exponential form. In case of optical fiber, that loss, okay, is expressed in terms of this decibel parameter, okay. So, if we do use this form, what happens, we can easily add up this losses, because logarithmic approach, no, logarithmic, we can easily add up, as let us say light travels through one fiber with alpha 1 as the loss, it gets coupled with another fiber with alpha 2 as the loss, etc. So, basically the total loss is alpha 1 plus alpha 2, okay, because log if you multiply, it will add up, right, it can be added up. So, losses can easily be added up. So, this formulation is useful to immediately estimate the right loss or right, power transmitted through the fiber, etc. So, some books they use this formulation, okay, wherein they will give basically this the right decibel. So, indirectly what it means, if you see our formulation, this loss is not per centimeter, actually it is decibel per centimeter loss, correct, you understood, right, decibel per meter. Okay, so sorry, I'll write it down here, instead of confusing you. Loss, if I represent what I told in the previous case, we represented it with per centimeter per millimeter, no, but when we consider, when we represent in terms of decibel, decibel per centimeter or decibel per meter, okay, loss, okay, it is represented by this form. So this alpha is basically alpha decibel, right, for us. This alpha is different from this alpha, right, that is okay, numerically it may be it is different, okay, so that you remember. Now tomorrow we will try to see, or before, just I will just describe this one more, this just to give you idea losses. If I am using multimode fiber, the losses, okay, decibel per kilometer, you can see the losses are high, single mode fiber the losses are less, okay, right. Over and above, depending upon wavelength also the losses will be different, right. I showed in the previous slide, I just gave you some approximate, but this wavelengths, are, although it is not mentioned here, so decibel, this may be visible range, okay, visible range. When we use 1.5 micrometer, this loss alpha decibel is around 0.2, 0.1, 0.2 decibel per kilometer, okay, it is very less. When I use 1.5 micrometer wavelength light passing through quartz glass or SiO2, right, crystalline, right, SiO2, I will observe very small loss, right, as compared to the general losses, okay. So this is just to give you an idea, it's no way you have to remember, but just to get an idea that multi-mode fiber, single mode fiber, these things will be less. Now next class, tomorrow's class, tomorrow means Thursday's class, we will talk about little bit more regarding when the light propagates through this type of waveguide structure. At the interface, core clade interface, there will be some losses. So how to estimate such losses in a single mode fiber, etc., and they have certain applications, right. Also we will try to see for biomedical application also it has, that is why we will try to cover such introductory aspects before we go to the next topic, okay, related to what are the types of light sources, etc. So we will be using them in our biomedical applications. So I will try to cover some of those light sources, but before we go into that topic, we will try to see some of the losses, very important right parameter, evanescent based right field and the losses associated with the waveguide structures, okay, we will try to cover. So thank you very much for this class. We'll I'll give you one just an right question, simple as such. Estimate the core diameter of a fiber, okay, for the fiber to be as an single mode fiber, okay, for wavelength of 1.5 micrometer, cutoff wavelength of 1.5 micrometer, okay, and refractive index maybe numerical aperture of 0.2, numerical aperture of 0.2, okay, wavelength lambda as 1.5 micrometer, okay. What should be the core diameter corresponding to that cutoff for a single mode operation? Are you understanding the problem?
What is the lambda?
Huh? Lambda value is 1.5 micrometer. Yeah. I am giving you directly numerical aperture. So, what example is problem or example is numerical aperture is 0.2, right, cutoff wavelength, okay, is or the wavelength for which I want the optical fiber with a numerical aperture 0.2 to be a single mode fiber. So, what I want to find out? Core diameter. Estimate, I would like to estimate the core diameter for a single mode operation, right. It is very simple, don't, no, not at all, it is much simpler than, right. It's so, right, if you can estimate and write it down on the paper, okay. So, we will estimate using V parameter, isn't it? The V should be less than or equal to 2.405 for a single mode operation, okay. So, let us assume maximum possible is 2.405 for a single mode operation, isn't it? So, if I assume this to be 2.405, and what is V? V is 2 pi r divided by lambda into numerical aperture, right. I know lambda 0, I know V approximately 2.405 for a single mode operation, I know numerical aperture, right, 0.2. Then what is the core diameter? So, 2r is, what is it approximately? So, around 6 micrometer or so, okay. Right.